Okay, third day. Let's get started. Today we're doing an example of gradient descent because I don't know if you watched the last one, you probably did not, but I explained it terribly and it probably made no sense. So we're going to go over it in more detail today with an example. So we'll use the most simple one, which is linear regression, because once you understand this, you'll be able to apply it to everything else. So let's start with what linear regression is. Now, I think this is something that most people cover even in high school, so I mean, it should be not too hard to follow along. So let's say I have 3 points, like maybe like 1, 2, 5, 4, and 3, 7. So I have 3 points, and I want to find some sort of line that models this as close as possible. Now, of course, we could add more points and we would have a better model. It would be easier to make a model. Okay, so now you're starting to see maybe we could draw some sort of line like this, right? And so this line would help us predict any new point. Like if you gave me a new x-coordinate, I could tell you, based on this line, what the y-coordinate will be. So it's like, I'm trying to find some sort of model to model the correlation between x and y, right? So we'll keep it simple for now and just stick with 3 points. But of course, once you learn this, you can apply it to as many points as you want. And we'll stick to 2 dimensions now, for now. But once again, you can apply this to as many dimensions as you want as you get more advanced. So to model this, we're going to need a few things, right? Obviously, we with brains can like intuitively draw a line. Okay, this thing should probably look something like this, right? But how do you mathematically show like that's the best line, right? How does a computer find that line that has no intuition? So we need to calculate, we need to find some way, we need to create some sort of function that lets us measure how good our line is. And we can do that with something called sum of squared errors. So there's a lot of different ways to do this, but we'll stick with the most simple one for now. So let me just give us a few variables, right? So y hat, or expected y, should equal ax plus b. Okay, we'll make this a little more machine learning-ish. So instead of saying y here, we'll say x1, and we'll say x0 here. And then we should say x1 should equal ax0 plus b. Actually, this doesn't make any sense, because this is not another feature, this is a label. Sorry. We'll keep it simple. Okay, cool. So now we have expected y equals ax plus b. So in this case, we have 2 parameters that we can adjust, a and b. So this is just our function for a line. This can create any line on 2 dimensions. So our point is, okay, so we've got 2 variables, and we need to find what the best 2 variables are so that we have the best line. Now let's define what best line means. We can use something called the sum of squared error. Okay, so don't be scared, this might look a little weird, but it's really not too bad. So let's ignore the sum for a second and just look at this thing, expected y minus actual y. And we'll say like maybe for the first point, so y naught minus expected y naught minus y naught. So what does this mean? So expected y will come from this function, right? So we'll get some value here, let's just say like 7, right? From our x that's given. So 1 is given to us here, and we want our expected y to be as close as possible to 2. And so the actual y is 2. So you can see our error, And also we need to do like a 1 over n here. So our error is going to be 5 for this one point, right? But if we look at the second point, expected y naught minus y naught, let's say we plug in some number, we put 5 in here, and we get some output back, and let's say it's like 15, right? But our actual value was 4. So our error for this one would be 11. Now the reason why we square this is, let's say like for our output we get 2, right? So for our expected y naught for this point, we got 2. And instead the actual value is 4. So what you can see here is we get a negative value. And we don't want negative values to be like opposite error, like if you're off by 2 below and if you're off by 2 above. We want to say that's the same amount of error. We don't want those two to cancel out. So that's why we have to square it. And so what this sum does is that it finds this error over every single point, right? So this will give you the mean square error. So this is our error function. Now, with this thing, we have a way of judging how good a line is. Because if I have like a line like this, right? If I have like a line like this. Okay, well, so for this value, my error is going to be however much this difference is. For this value, my error is going to be massive, and for this value, my error is going to be massive. So you can see this is a terrible line, right? Like this is a terrible model. However, if we were to have like a different line, let me get a different marker actually. So let's say like a beautiful line, right? One that's really nice. Well, now you see our error here is almost 0. Our error here is a lot less, and our error here is a lot less. And so basically, we need to find some way of minimizing this function. Because this function tells us how much error we get, and we need to find the smallest possible one, right? Okay. So let's see, how do we do something like that? Basically, we need to be minimizing this function. All right, so let's do that. So there's 2 ways to do this. The first is with gradient descent, and the second is just solving something. So I'm going to assume that you've done at least calculus before, all right? So in calculus, we know if we want to find a minimum of a function, we can take its derivative and set it to 0, right? So if I have a function like y equals x squared, and I want to find the minimum value here, I can take its derivative, right? And now, when the derivative is equal to 0, that means that the function is almost not changing at this point, right? And if it's almost not changing, that means it has to be a maximum or a minimum. Otherwise, like if the function was changing at that point, it couldn't be a maximum or a minimum. So all maxes and mins for a smooth function will have almost no change. Like you can't imagine a function with a maximum or a minimum that has a lot of change. Because if it's changing a lot, then it's not the maximum or a minimum, right? So then we just set this derivative equal to 0. And then we see, okay, so when x equals 0, there's either a minimum or a maximum. The way we tell whether or not it's a minimum or a maximum is by taking the second derivative and then seeing whether that's positive or negative. So if we take the second derivative, which is equal to 2, if this is positive, that means it's a minimum. And if this is negative, that means it's a maximum. I'm going to leave it up to you to figure out why that is. Try it. This is left as an exercise for the audience. That's whenever a teacher doesn't know what they're talking about, they just say that. So yeah. I'll have to go back and review that as well, actually. Anyway, so now we just need to apply the same idea to this thing, right? So we need to figure out when this derivative, the derivative of this function is equal to 0. Okay, so how do we do that? Well, all right, so we start by plugging in this here. Because if we're trying to solve for a and b, well then we have to know, right? We have to have our parameters in here. And so this is a function. A loss function is what it's called, but we can call it an error function. So error dependent on a and b is equal to this. So this is where the multivariable comes in because we've got two parameters here. But I mean, if you know derivatives, like this shouldn't be too much harder. I'll explain as we go. Okay. Alright, so let's start simplifying, right? So this is our function, right? Which is way uglier now, but I mean, it's still the same thing, right? So now we can just take the derivative of this, right? And so this is where it gets a little complex because we have to take the derivative, we have to take the partial derivative. And then we can find the gradient. But first we need to take the partial of both. So first we need to take the partial of a. How do you do that here? I'm going to be completely honest, I'm not quite sure. So actually let's just plug in these absolute values and then it'll be like I don't know if you can take the derivative of these sums because like this is a abstract version of our problem, right? So actually, yeah, I don't even think this is differentiable. You have to like plug in these values first. So let's do that. And so now, well, okay, so now this is simple, right? So if we have b in terms of a, well then basically we only have one function. Well, we have a function of one variable, right? So let's solve for b actually. So b should equal 34 over 36a minus 5. And this is equal to 17 over 18a minus 5 equals b. Cool. So what can we do with this result? Well, we can plug it back into this monster and then solve that, right? Solve that for 0. So let's do that. I'm going to I'll skip ahead. Okay, so I skipped ahead to the interesting part and we're back to here. And so now we're going to pull out the calculator and do this final step together. Alright. There's the work. Bam! A equals 3.76. So what does B equal? Well, B equals 17 over 18. Look, we found it. And does that make sense? Let's just take a cursory look, right? Yeah, more or less. It more or less makes sense. I think maybe it's a little skewed, as in like it looks like this. Like we found our line. We found our line. Y equals 3.76 x minus 1.45. Cool. Guess what? None of that was gradient descent. All of that was just regular linear, that's called like least squares estimation. So just finding the 0 to the partial derivative. But for neural networks, guess what? It's not this fun. Even just for two variables and for like the simplest error function, loss function you could think of, it took us like 20 minutes, right? Guess what? Neural networks have equations, functions that are like, yeah, across this whole whiteboard and maybe a few more, because like I said, hundreds of layers, millions of layers. So each of those adds another operation. And so you have to use the chain rule to find all of those derivatives. That's when we start using gradient descent and backpropagation, because although it's possible to find it for 0, it would take millions of years. So that's why we need to use these tools, right? And so I guess we'll cover that. I guess we'll never cover that. Go search it up. Okay, well, we did least squares. We didn't get to gradient descent. But basically, instead of finding the derivative and setting it equal to 0, you find the derivative and then you just plug in a single point, and then you plug in a point for this original function, and then you find the derivative of that. And so if the derivative is positive, that means the function is growing. And you want to go the opposite direction, so you take the negative derivative. And since you can have infinite dimensions, you just call it a gradient and you call it a day. Okay, thank you for watching.